Imagine this. You're standing in a huge field of potato plants.
Yeah.
But something's wrong. Like our farmer, John, last spring. The plants looked weak. The potatoes were tiny. The whole harvest was, well, way down.
Yeah, a real problem. And John knew deep down it was something in the soil, some kind of nutrient missing. But which one? How do you even figure that out?
Exactly. And that's where, believe it or not, chemistry comes in. Understanding the basics, the elements, the atoms, it's actually the key.
Welcome to the deep dive. Look, today we're cutting right through the complexity. We want to show you how knowing about elements and atoms isn't just, for passing exam.
Right.
It's fundamental. It explains why John's potatoes failed, how your own body works, the phone in your hand, pretty much everything.
So we're going to unpack these core ideas, really focusing on how they connect to health, to life sciences, making it relevant for you.
Let's dive in. Elements. We talk about them all the time. Oxygen, gold, carbon. But what are they fundamentally?
The pure stuff, right?
Yeah.
The basic ingredients you can't break down any further chemically.
Precisely. There are 118 known. About 88 occur naturally. And they're everywhere. Aluminum in your soda cans, gold in jewelry.
Titanium in a tennis racket.
Yeah, or carbon fiber in a bike. But crucially, think about your body. Calcium, phosphorus. They literally make up your bones and teeth. Iron and copper. Essential for your red blood cells to carry oxygen. And iodine, just a tiny trace. But your thyroid gland absolutely needs it to control your metabolism.
It's amazing how these chemical bits are running the show inside us.
Totally. And chemists have a shorthand, right? Chemical symbol.
Yeah, the 1 or 2 letter codes, like H for hydrogen, O for oxygen.
Exactly. And the capitalization is super important. Co, capital C, lowercase o, that's cobalt, a metal.
But CO, both caps.
That's carbon monoxide. 2 different elements bonded together, a poisonous gas. Big difference.
Wow, okay. So small detail, huge consequences, which brings us down to the atom itself. The smallest piece of an element that's still that element.
Right. The idea is ancient the Greeks talked about atomos, meaning uncuttable. But it was John Dalton, back in 1808, who really put the science behind it.
His atomic theory. What were the key points again?
Well, basically, all stuff is made of atoms. Atoms of one element are the same, different from other elements. They combine in fixed ratios to make compounds, and in reactions, they just rearrange. They aren't created or destroyed.
Still pretty solid ideas today, though we know now atoms aren't quite identical, and they're made of smaller bits.
True. And you can't see them with your eyes, obviously. But pack billions together, and you see the element's properties like a gold bar shining.
And now we can actually see them, sort of. With those fancy microscopes.
Yeah, the scanning tunneling microscope, or STM, it can image individual atoms. It's incredible technology.
So inside the atom, what are those smaller bits?
The subatomic particles. 3 main ones. Protons, neutrons, and electrons.
Okay. Protons are positive.
Yep, protons have a positive 1+ charge. Electrons have a negative charge. And neutrons.
Neutral, no charge. Makes sense.
Exactly. And these charges dictate so much. You know how your hair might stand on end if you brush it on a dry day, like charges repelling?
Or clothes clinging out of the dryer.
That's unlike charges attracting. It's the same fundamental force operating inside atoms. Protons and neutrons are crammed into the nucleus, this tiny, super dense core.
Tiny but heavy.
Very. But the electrons, they're moving rapidly in the space around the nucleus. That's what gives the atom its volume, makes it mostly empty space, actually.
It's wild to think about. How did they figure all this out?
It was a process. J.J. Thomson found evidence for the electron around 1897. Then Rutherford's gold foil experiment, maybe 10 years later, was huge.
That's the one that showed the nucleus, right? Blew up the old plum pudding idea.
Exactly. Showed there was a dense positive center. The neutron came along a bit later to explain the extra mass in the nucleus. Protons and neutrons have roughly the same mass, about 1 atomic mass unit, or AMU. Electrons are way, way lighter.
So light, you often just ignore their mass in calculations.
Pretty much. Sometimes you'll see AMU called a Dalton, especially in biology circles. Same unit.
Okay, so we have all these different elements made of atoms with protons, neutrons, electrons. How do we keep track? It feels like chaos.
But there's order. Beautiful order, thanks to the periodic table.
Mendeleev, the Russian chemist.
The very same. Dmitry Mendeleev, 1869, he took the 60 or so elements known then and arranged them. He saw patterns.
By weight, wasn't it? And properties.
By increasing atomic mass, initially and crucially, grouping elements with similar chemical behaviors. He even left gaps for elements that hadn't been discovered yet, predicting their properties.
Genius. And that led to the table we use today with all 118 elements.
Yep, it's a grid. The vertical columns are groups, sometimes called families. Elements in a group act alike chemically.
Like group 1, the alkali metals. Sodium, potassium. Ones that go boom in water.
Exactly. Soft, shiny metals, super reactive. Then group 2, alkaline earth metals like calcium, magnesium, still reactive, but less so.
And the rows across are called
Periods. As you move across a period, the properties change in a predictable way.
Got it. Any other important groups?
Oh yeah. Group 17, the halogens, fluorine, chlorine, bromine, highly reactive nonmetals, always looking to pair up.
And the ones that don't react. Group 18.
The noble gases, helium, neon, argon, they're very stable, very unreactive, happy on their own, chemically speaking.
Okay, and there's that sort of staircase line on the table.
Yeah.
The zigzag.
Ah, yes. That's the great divide. It separates the metals from the nonmetals.
Most elements are metals, right? To the left.
Overwhelmingly, metals are usually shiny, solid, except mercury. You can shape them. Ductile means pull into wires. Malleable means hammer into sheets. And crucially, they conduct heat and electricity really well.
Essential for, well, everything electronic.
Absolutely. Then to the right of the zigzag, you have the nonmetals. Think carbon, nitrogen, oxygen, sulfur. Generally, they're not shiny, not malleable, poor conductors, often gases or brittle solids.
And what about the ones right on the line?
Those are the metalloids. Boron, silicon, germanium. They're in-betweeners. They have some properties of metals, some of nonmetals.
Like silicon, isn't that used in computer chips?
Precisely. Because metalloids are often semiconductors, their ability to conduct electricity can be controlled, turned on and off. That property is the foundation of all modern electronics.
So metal, non-metal, metalloid, distinct categories based on properties. Cool. Let's go back inside the atom. You mentioned numbers are key.
Absolutely. The atomic number. This is the defining number for an element. It's simply the number of protons in the nucleus.
Every carbon atom has 6 protons.
Every single one. If it had 7, it wouldn't be carbon anymore, it'd be nitrogen. The atomic number is the element's identity card.
And in a neutral atom, it also tells you the number of electrons.
Correct. Equal number of positive protons and negative electrons means no overall charge.
Okay, so that's atomic number. What about mass number?
Mass number is different. It applies to one specific atom. It's the total count of protons plus neutrons in that atom's nucleus.
So it tells you how heavy that particular atom is.
Essentially, yes. And if you know the mass number and the atomic number, protons, you just subtract to find the number of neutrons. Simple as that.
Mass number minus atomic number equals neutrons. Got it. This must be related to isotopes then.
Exactly. Isotopes are atoms of the same element, so they have the same number of protons, same atomic number, but they have different numbers of neutrons.
Meaning they have different mass numbers.
Perfect. We write them using the element symbol, with the mass number up in the top left corner and sometimes the atomic number in the bottom left. Like magnesium, it exists as Mg24, Mg25, Mg26. All have 12 protons, but 12, 13, or 14 neutrons, respectively.
Okay. And that explains why the masses on the periodic table aren't nice whole numbers.
You got it. The mass shown on the table is the average atomic mass. It's a weighted average of the masses of all the naturally occurring isotopes of that element based on how common each one is.
So if chlorine's average is 35.45 mu,
it tells you that the isotope chlorine-35 is much more abundant in nature than chlorine-37. The average is closer to 35.
Makes sense. It's like a weighted grade average.
Good analogy. And speaking of different forms, even just arranging atoms of the same element differently can create materials with wildly different properties. Carbon is the classic case.
Diamond and graphite, right? Both just carbon.
Pure carbon. But diamond is incredibly hard, transparent. Graphite is soft, black, slippery. It's in your pencil lead. The only difference is how the carbon atoms are locked together in the crystal structure.
Mind-blowing.
Mm-hmm.
Are there other forms?
Oh, yeah. More recently discovered ones like Buckminster fullerene, they call them buckyballs. Imagine a soccer ball made of 60 carbon atoms.
Wow.
And carbon nanotubes, basically rolled up sheets of graphite. Incredibly strong and light.
What could you even do with stuff like that?
The potential is huge. Super strong, lightweight materials for planes or cars. Materials that conduct heat incredibly well. Tiny components for computers, even medical uses. Imagine nanotubes delivering drugs right to a specific target cell in the body.
That sounds like science fiction.
It's cutting-edge science driven by understanding how atoms arrange themselves.
Okay, so structure is key. What are the electrons? You said they're responsible for bonding and reactions.
They absolutely are, especially the outermost ones. But first, electrons don't just orbit randomly. They exist in specific energy levels, like shells around the nucleus.
Quantized levels, meaning they can only be at certain levels, not in between.
Exactly. Think of it like shelves on a bookcase. An electron can be on shelf 1 or shelf 2 or shelf 3, but never floating halfway between shelf 1 and 2. The lower shelves, closer to the nucleus, hold fewer electrons and have lower energy.
And electrons can move between these levels.
Yes, but it takes energy. If an electron absorbs the right amount of energy, it can jump up to a higher, unoccupied level.
And when it falls back down?
It has to release that extra energy. Often it releases it as light, a specific color or wavelength of light corresponding to that exact energy drop.
Is that like how streetlights work? Sodium lights are yellow.
Precisely. The yellow glow is the light emitted when excited electrons and sodium atoms fall back to lower energy levels. Same principle for the red glow of neon signs.
Huh. Okay, so electron energy levels explain colored lights. Does this connect to health stuff too?
Big time. Think about sunlight, specifically ultraviolet or UV light. UV has high energy.
Enough to zap electrons to higher levels in our skin cells.
Exactly. That initial energy absorption can trigger a cascade of chemical reactions, some of which are damaging. That's what causes sunburn, contributes to skin aging, and can even damage DNA, potentially leading to the skin cancer.
Yikes. And some medicines make you more sensitive.
They can, yes. Certain antibiotics, acne treatments like Accutane, they can increase your skin's reaction to UV light, basically making those electron jumps happen more easily.
But light can also be used for good, right?
Definitely. We can harness specific wavelengths. For seasonal affective disorder, or SAD, some people benefit from light boxes using blue light around 460 nanometers. It seems to help regulate brain chemistry.
And for babies with jaundice.
Blue light, again, usually 390 to 470 nanometers. It's called phototherapy. The light energy helps convert the bilirubin, that yellow substance causing the jaundice, into a form the baby's body can easily get rid of. It's a direct application of controlling electron energy states.
Fascinating. So not all electrons are involved in this jumping and bonding stuff, just the outer ones.
Primarily, yes. We call those the valence electrons. They're the electrons in the outermost occupied energy level. They're the ones that interact with other atoms.
And they determine how an element behaves chemically.
Largely, yes. Their number and arrangement dictate how an element will bond, what kind of ions it might form, its general reactivity.
Is there an easy way to know how many valence electrons an element has?
For the main group elements, the representative elements, yes, the group number using the 1A to 8A system tells you directly. Group 1A metals have 1 valence electron, group 2A have 2, group 7A halogens have 7.
And group 8A, the noble gases, have 8, except for helium.
Exactly. Helium only has 2, filling its first energy level, but the others have 8, a very stable arrangement, which is why they're so unreactive. There are even simple diagrams, Lewis symbols, that just show the element symbol and dots for its valence electrons.
So the periodic table isn't just organized, it predicts behavior based on electron structure.
That's its power. It reveals periodic trends, predictable patterns and properties as you move across or down the table.
Like atomic size. Do atoms get bigger or smaller?
Okay, good one. Atomic size generally increases as you go down a group.
Why is that?
Because you're adding more electron shells, more energy levels. The outermost electrons are simply farther from the nucleus.
Makes sense. And across a period, left to right.
It actually decreases, which seems weird at first because you're adding electrons.
Yeah, why smaller?
Because you're also adding protons to the nucleus in the same period. That stronger positive charge pulls all the electrons, including the outermost ones, in tighter. Stronger pull, smaller atom.
Huh. Okay. What about how easily an atom loses an electron? Is there a trend for that?
Yes, that's ionization energy, the energy needed to remove the outermost electron.
So down a group where atoms are bigger and the electron is farther away. Easier to remove.
Easier to remove. So ionization energy decreases down a group, less energy required.
And across a period, harder to remove because of that stronger pull.
Exactly. Ionization energy increases across a period. Metals on the left have low ionization energies. They lose electrons easily to form positive ions. Nonmetals on the right have high ionization energies. They tend to hold on to their electrons or even gain more.
And the nodal gases must have the highest. since they're so stable.
The highest ionization energies in their respective periods, yes, they really don't want to lose an electron.
This relates to being metallic, doesn't it?
Directly. Metallic character basically describes how readily an element behaves like a metal, which primarily means how easily it loses valence electrons.
So it increases down a group, easier to lose electrons, and decreases across a period, harder to lose electrons.
You've got it. These trends help us predict chemical reactions and understand bonding.
Okay, this is making sense. We've gone from the basics to these patterns. How does this all tie back to, well, us, to health, and to John's potatoes?
Right, the practical application. It's amazing, really. Out of all those elements, humans only need about 20 for survival.
20, that's it.
Roughly. 4 make up 96% of our body mass. Oxygen, carbon, hydrogen, nitrogen, the absolute building blocks for water, proteins, fats, DNA, everything. Hydrogen, for instance, is key in stomach acid, hydrochloric acid, HCl.
Okay, the big four. What else?
Then you have the macrominerals. We need them in larger amounts. Calcium and phosphorus for bones and teeth, obviously, but also potassium, sodium, chlorine for nerve signals and fluid balance, magnesium for enzymes, sulfur and protein.
These are the electrolytes you hear about.
Many of them, yeah.
Good.
Essential for electrical activity in the body. Then there are the microminerals or trace elements, needed in tiny, tiny amounts.
Like iron.
Iron for hemoglobin in red blood cells is critical. Zinc for the immune system. Iodine for thyroid hormones, which control metabolism. Copper, manganese, selenium. They all play vital roles, often helping enzymes work correctly.
But isn't stuff like arsenic poisonous?
It absolutely can be, but fascinatingly, arsenic, chromium, selenium, they are required in extremely small trace amounts. It's all about the dose. Too little is bad, too much is toxic. Chemistry is all about balance.
Which brings us back to John's field. Plants need nutrients too.
Just like us. They need macronutrients and micronutrients. The big three for plants are usually nitrogen N, phosphorus P, and potassium K.
NPK. You see that on fertilizer bags.
Exactly. John's potatoes, with the brown spots and poor growth, were showing classic signs of potassium deficiency. Potassium is vital for plants making proteins, photosynthesis, activating enzymes, managing water.
So his soil test showing low potassium, below 100 parts per million, confirmed it.
Confirmed it. And the solution was chemical. He added potassium chloride KCl as fertilizer, not just randomly, but at a calculated rate, about 170 kilograms per hectare based on the soil needs.
And it worked.
It improved the yield and quality significantly. That's chemistry, applied directly, improving our food supply, which directly impacts our health.
It shows how vital understanding these elements is, but also how things can go wrong. You mentioned toxicity. Mercury is a bad one, isn't it?
A really stark example. The historical poisonings in Minamata and Niigata, Japan, were devastating. Industrial waste dumped mercury into the water.
And it got into the fish.
Yes, and it biomagnified up the food chain. People who ate a lot of local fish suffered severe neurological damage, birth defects, terrible consequences. Mercury ions mess with proteins and stop cells from working properly.
And understanding that chemistry led to regulations.
Yes. Agencies like the FDA now set limits for mercury in seafood, advising caution with fish high on the food chain, like shark or swordfish, where mercury tends to accumulate. It's chemical knowledge being used for public safety.
Wow. We've covered a lot of ground here. From John's potatoes and basic elements.
All the way through atomic structure, the periodic table, electron behavior.
And landing squarely on how it impacts our health, our food, and even environmental safety.
It really shows that chemistry isn't just formulas on a page. It's the fundamental operating system of the world, you know? Understanding even the basics gives you a powerful lens to see how things work.
Absolutely. It's a shortcut to being truly informed about so much. So here's something to think about. Given how these basic building blocks and their energy states explain so much, what other everyday things, maybe biological processes or even just weird phenomena, could be explained by simple atomic or electronic shifts if we just looked closely enough?
A great question to ponder. We really hope you found this dive into the chemical world useful and maybe even a little exciting.
Thanks so much for joining us on this deep dive. Until next time, keep exploring.